we are going to do the products of this reaction. So let's see what it is. This is a ketone, and I have an alcohol, acidic conditions. So here we have a ketone, alcohol, acidic conditions. So that reaction is the same reaction that we saw for hemiacetal acetal formation. So let's do that. First step is protonation of the oxygen at the carbonyl carbon. So here's OH. So I'm going to do this. We are under acidic condition. That is making the carbonyl carbon more electrophilic. In this time, I don't need to have an alcohol, an external molecule. I have the alcohol in the same molecule. So this is an intramolecular attack. So nucleophilic attack, and I'm moving that. What we need to be paying attention is now to the structure of the product. So let's see. Counting carbons here, I'm going to make a cyclic structure that will have 1, 2, 3, 4, 5, and 6 with the oxygen. Okay, now let's start doing that. So the carbon that let's do here on the top, we'll have an OH and we'll have a metal group. So that's that. The rest here, the O will be attached here. So this is that. Well, I can do numbers actually. Let's number this 1, 2, 3, 4, 5, and 6 with the oxygen. So we can see that we have made a bond between carbon 1 and the oxygen. So this is 1. That was 6. And then we'll do 5, 4, 3, and 2. Okay, so 1, 2, 3, 4, and 5. Now I have in this structure, I have an extra H, so because the oxygen 6 had an H. So that's formal positive. And I need a proton transfer step here to say that we have water space, for example, if this in aqueous solution. So proton transfer and electrons back here. So I'm going to form OH here. I have a metal, and then I have the O right here. This, if we look at the structure, has an OH and an OR. All of that is an O in carbon attached. So it is an hemiacetal, but it is cyclic. So cyclic, spelling. Cyclic hemi, because I have OH and R. Hemiacetal. Okay, so that reaction is, by the way, reversible under acidic conditions. Same thing that we did when we analyzed the mechanism starting here. So stable, unstable, it will be unstable, so reversible under acidic condition, but stable under basic, same thing. So, but this is an hemiacetal. That reaction is important when it is observed. These hemiacetals are isolated actually for sugars. Sugars are, and let's draw a structure of a sugar here. Gonna draw the skeleton OH. Gonna draw a sugar. Let's see, so using the functional groups here, we have several OHs, and here you have an aldehyde functional group. So this is glucose in the open form. So glucose, and glucose is a polyhydroxy, so several hydroxy group aldehyde, polyhydroxyaldehyde. So that's the open form, but glucose exists in the hemiacetal, cyclic hemiacetal form. So what we're doing here, again, under acidic condition, even traces, we will have that. So now you will have the attack by an internal oxygen similar to that. So if we do the attack with that, it will be too small a ring or that. So if we did it with this, we're going to have one. Let's do the cyclic. It's going to form a cyclic structure of 6 carbons, 6-member ring. 1, 2, 3, 4, 5, and 6. So this is the oxygen that will do the attack. Why that? Because the most stable rings will be a 5 and 6-member ring. This will be too large if we do it with that. Here, these is the ideal size. So let's put the number 1 here. So I'm gonna have, once it's protonated, I'm gonna have the nucleophilic attack over here. And we already counted the members, but this time I'm going to draw it slightly different. Instead of drawing it like that, I'm going to draw it in the form of a chair. But it's like when you guys studied cyclohexane conformation, same, but now I have an oxygen. And I have OHs and several carbons, so I will have OH here. If you guys recall these positions, this is equatorial, this is axial. And here I will have another equatorial. And finally, this is CH2OH. So I'm going to have that here like that. And if you notice, this is carbon number 1, which in sugars is called the anomeric carbon. So, and this is OH, OR. So it is an hemiacetal. So again, it's a cyclic hemiacetal. Those structures are, sugars do that. Always they are in equilibrium on low closed form, the cyclic hemiacetal, and open form. Also that it produces the epimerization of that carbon. That oxygen can be in a couple positions, not the topic here. But we need to know that hemiacetals, the hemiacetals that can be isolated are those of sugars, and all other hemiacetals are rarely isolated. We go straight to the acetal. And important points again is that those reactions are reversible under acidic conditions, like all of that, but the acetals are stable under basic conditions. It's not going to reverse. And that is allow us to design synthesis using this structure, cyclic hemiacetals, like an example we did in another video, to protect carbonyl groups and do other chemistry.